questions on the homework that's due today?
Question 10, the last one.
That's, sounds really familiar. 675. So, number 10 asks for the length of the function e to the x plus e to the minus x over 2 on the interval negative log of 2 to log of 2. So this is mostly about doing the algebra carefully. Right? So our formula says this should be the integral from negative log of 2 to log of 2 of, this is where a formula comes in, 1 plus, I'm just going to say here, the derivative of our function squared. And we can immediately simplify this a little if we note that this is an even function. You don't have to do this. This is just to make life a little simpler. But this is an even function, and we're going from negative a to positive a. So this becomes just the integral from 0 to log of 2 times 2 of whatever we have in here. Okay, this is the piece that we're going to need to do some manipulation on. So let me just work on this for the moment. First of all, f prime of x is just e to the x minus e to the minus x over 2. Again, you don't need to know about the hyperbolic functions, but it just so happens that this is the hyperbolic cosine whose derivative is this, which is the hyperbolic sine. So we have the square root of, and I'm going to write this for my own purposes as 4 over 4. You'll see why in a second. We need to square this, right? We need to square it. So that becomes e to the 2x minus 2. This e to the x times e to the minus x is 1. Plus e to the minus 2x over 4. You know, sometimes I wonder about these problems we give you where they just work out perfectly. It's like, too nice, right? The world isn't always like that. Sometimes you can make them work out if you really beat on them hard. But often you're just stuck with going back to numerical integration. But we're not really, we don't do that much numerical integration because once you know how to do it, you just plug it in your computer or your calculator and it does it. Okay, we rearrange this a little. 4 fourths minus 2 fourths is 2 fourths. So and hopefully at this point, this is recognizable. This is the hyperbolic cosine squared, or e to the x plus e to the minus x over 2 squared. So this becomes the square root of e to the x plus e to the minus x over 2 squared. And of course, the square root and the square cancel, and we're back to the hyperbolic cosine. All right, so let's plug this in over here. e to the x plus e to the minus x over 2 dx. And of course, the antiderivative of this now just goes back to being the hyperbolic sine, which is e to the x minus e to the minus x over 2. Let's keep our 2 here, and this goes from 0 to the log of 2. Now, I hope at this point, those of you who have forgotten your 48C logarithms, I hope you've reviewed enough to know that e to the log of 2, e to the natural log of 2, is just 2. So we have 2. Now we have e to the minus log of 2, which is just 1 over e to the log of 2, which is just 1/2. And we've got another 2 here. These cancel, so this just becomes 3/2. It's nice when they work out that way. I think we did another problem like this where there were some coefficients on e to the x and the minus x, and it still worked out. Just plan carefully to do that. Okay, other homework questions? Okay, if you want to hand it in during the break, put your homework up on the table, not now. Right. So, I'm not quite sure where we left off. We were starting to talk about polar coordinates. You should know what polar coordinates are. Typically, we use the variables r and theta because they evoke the idea of a radius and an angle. We have some conversion factors, conversion formula to go from xy to r theta. Well, r is just use the Pythagorean theorem. Theta is usually inverse tangent of y over x. But you have to look at the values, the signs of y and x to figure out which quadrant it's in. Again, this is 48C, you should know this. To go the other way, xy, we just use the familiar formulae, x equals r cosine theta, y equals r sine theta. And then we started talking a little bit about what a polar equation might look like. Polar equation would have some expression with, we don't have a syntax for expression with, but with thetas and r's, and more often than not, it's just going to be r equals some function of theta, such as cosine of theta. So if r is the cosine of theta, what does that look like? Well, at zero angle, it's just going to be 1. Right? And straight up, at pi over 2, it's going to be 0. And And what is it in between? So the square root of 2 over 2. It's going to look like this. If you keep going from pi over 2, it's just going to circle around, and you can see magically it's just a circle. If you look at something a little more interesting, r equals cosine of theta plus 1. I think we got this far. We get a cartoid, which is heart-shaped. So what would that look like? So at 0, it's just going to be 2. And at pi over 2, it's going to be 1. So at pi over 2, the radius is going to be 1. I think I talked a little bit about the fact that if you have an even function here, it's a little different from x and y. It's even, and it's going to be symmetric across the x-axis. We know we have a point here, too. I guess at pi, way out over here, cosine becomes -1, so it becomes 0. But it does it kind of slowly. Kind of does it like this. And you get your inverted Valentine's Day symbol heart. Okay, so what we're interested in here is being able to do some integration to find the area in polar coordinates on with some function. And I think we may have talked about this a little too. The strategy is we have some function f of theta, or r equals f of theta, and we want to find the area in through some set of theta here, theta 1 through theta 2. And so we look at a very small angle. Call this delta theta. And the very small area here we find by using formula for the area of a circle. All right, what do I mean by that? Well, the area of a circle is what? It's 2 pi r, or we could think of it as, I'm sorry, that's not what it is. It's pi r squared. We could think of that as theta circle times r squared. It's theta circle. Theta circle is 2 pi, right? That's how far it is around the circle, but over 2. So if you plug in 2 pi here, you just get this formula. So that's the area, this just magically, if r were a constant. But, of course, r is not a constant. So instead, we're going to integrate from theta 1 to theta 2. Times, let's substitute for r squared, f of theta squared over 2 times d theta. thinking there's something else here. Yeah, there's another way to look at it. If you think of this little piece here, delta theta, you know this is r, or f of x, which is f of theta, which is r. If you thought of this as a triangle, what's the length of the base here? Everyone remember the definition of radian measure is the length here, S over R. So this little length here, B, is just R times, or again, f of theta times delta theta. So if the area of the triangle is just 1/2 base times height, well, the height again is R, so this just becomes f of theta squared over 2 times delta theta. And again, if we plug this in and make delta theta much smaller, we get the same thing. Again, this is the area here of, what we're integrating. Okay, some difficulties you may have with this is you have to be careful about what your theta are, all right? We're plugging theta into a function, right? Right? But if we add, say, 2 pi to theta, we're going to get the function with the same value, but it's not necessarily the same thing, all right? In other words, if I say I want to integrate some function from 0 to pi over 2, that's not the same thing as integrating from 0 to 2 pi plus pi over 2, f of theta. That's because, well, assuming this function is periodic, which it may or may not be, we're still integrating the area all the way around and then back again, and that's going to give us a larger answer. So we have to think a little more clearly about these when we're setting up our problem. The other difficulty we're going to run into is, as you'll see in one of these problems, some of these problems, sometimes you have to do a calculation to find out what the limits of integration are. And we'll go over that. Okay, but again, keep this formula here in mind. It's going to come in useful. Okay, let's start with a simple problem. Did I do this problem? R equals cosine 2 theta, and over the theta interval, negative pi over 4, pi over 4. So our formula tells us this is the integral from negative pi over 4 to pi over 4 times what are we integrating here? We're integrating cosine of 2 theta squared over 2 d theta. It'd be better to put the 2 over here. All right, so we're going to have a little bit of a workout with our knowledge of trigonometry. Does anyone know what we need to do with cosine squared of 2 theta? There's an identity we're going to use. We could start with cosine squared x plus, no, that's not it. We start with cosine 2x equals what? Cosine squared x minus sine squared x, or 2 cosine squared x minus 1. And solving for cosine squared, we get cosine of 2x plus 1 over 2. So how is that useful here? Well, we don't have x, we have 2 theta, but that's fine. We just substitute 2 theta for x, and we're going to get cosine squared 2 theta. It's going to be cosine 2 theta, or 4 theta, plus 1 over 2. And that's what we're going to do here. So I'm just going to leave off the limits for the moment. So this is cosine of 4 theta over 2 plus a half theta. Okay, antiderivative of cosine 4 theta. You could do a substitution, but you should be able to do this in your head at this point. This is going to be the sine of 4 theta over what? Anybody? Should be doing these in your dreams by now, right? And then this is just theta over 2. And we take that from pi over 4, negative pi over 4 to pi over 4. All right. Sine of 4 theta, plugging in pi over 4, that's just sine of theta, which is 0 plus pi over 4 minus pi over 4 times 4 is minus pi. Sine of minus pi is 0 minus a minus. Oh, did I? Sorry. Forgot that extra 2. Minus a minus pi over 8. So minus becomes plus. So this should be just pi over 4.
And times 1/2.
Did I leave that a half? Where's my half? I know you're right, but oh, this is the half I left off. Okay. There was a 2 here and there's a 2 here, so there should be 4s here. Thank you. And this becomes 16, and this becomes 4, this becomes 16, this becomes 16, so this becomes 8. Okay, that's a simple problem that even I can't do up here in front of the blackboard. Let's look at something a little harder. I want to turn on the visuals for a second. Maybe that'll come on in a minute. So here's where your calculator comes in really handy to visualize what we're looking at. The next problem is we have two functions. F of theta equals 3 sine theta, and g of theta equals 1 plus sine of theta. We know this is going to be a cartoid. We don't know quite what that is yet. We will find out. So, are we there yet? Okay. All right, so follow along. So, again, I have to put my calculator in polar mode. So I use the mode key, set point to pole, and now I can put in my polar equations. 3 sine, and I just hit, this xt theta n key. It automatically knows. All right, so no surprise, 3 sine theta appears to be another circle. Let's adjust the window a little here. Let's see, x min, say, -5. How can I adjust the y? Oh, it's further down. So, -5. You don't have to do this if you can see already what's going on. I just want a nice pretty picture of that. I don't like that because it's a circle, but it doesn't look like a circle, so I'm going to try this. Okay, zoom squared, and let me zoom in a little. Nope, too much, zoom out. Okay, the next function is 1 plus sine theta. Okay, so that would be nice to see that a little better, bigger, so we'll zoom in anyway. All right, so one of these is a circle, and one of them you see is a cartoid. And we are looking for a region that lies inside the circle and outside the cartoid. So here's my circle, and then here's my part. So inside the circle, but outside the cartoid. Which means I want to integrate from this angle, call that theta 1, to this angle, theta 2, and find a function that describes this, the radius, the different areas. Okay. So, again, the first challenge is to find these points here. You can see it's symmetric, so we really only have to find one of them. And how do we do that? We set 1 plus sine theta equals 3 sine theta. So we get 1 equals 2 sine theta. Or sine theta equals a half. Okay, does anyone know for which theta sine theta is a half? That's that 30, 60, 90 triangle thing, right? There's 60, there's 30, and 1/2 over 1, square root of 3 over 2. You see so often. Okay, so 30 degrees is pi over 6. Well, that's this one, right? Yeah. So we're going to integrate from pi over 6 to 5 pi over 6. But now we've got kind of two things going on. There's the area, the inner area, which we want to remove from this outer area, right? So using our formula, we take 3 sine theta squared over 2. That's this bigger area, right? The circle, part of the circle. And we can subtract the smaller area, which is 1 plus sine squared theta, I'm sorry, 1 plus sine theta squared over 2 theta. All right. Anyone see the obvious? Well, I don't know if that's obvious. I don't know if that really helps any. I'm thinking, we know this is symmetric, so we know if I just integrate from here to pi over 2, that's half. So we can just double that. But I don't know if that's actually going to help us any, so I'm not going to do that. I think in the end we're going to have to evaluate sines and cosines. Okay. So what do we get here? We have 9 sine squared theta over 2 minus sine squared theta plus 2 sine theta plus 1 over 2. So that becomes 8 sine squared theta over 2, which is just 4 sine squared theta, minus 2 sine theta over 2 is sine theta minus 1/2. All right. Theta. This looks familiar, doesn't it? We just did something like this. Cosine squared theta equals, I'm sorry, cosine 2 theta equals cosine squared minus sine squared, 2 cosine squared minus 1, or 1 minus 2 sine squared theta. So now if we solve, we're going to get cosine of 2 theta minus 1 equals 2 sine squared theta. But we really need 4, so let's just multiply this by 2. Oh, minus, thank you. Cosine theta minus 1 over minus 2, and then we'll get to 4. Right? Okay, so let's plug that in. Minus 2 cosine 2 theta plus 2 minus sine theta minus 1/2. Well, it's just 3/2. Now we have to find the antiderivative, right? We're still in an integral here. So this is -2 sine 2 theta over 2. Minus cosine, so plus cosine theta, plus 3 theta over 2. And that would be a good time to put in our okay. This gets more and more fun, right? Told you you're going to have to know that trick. Right? Okay, so sine of 2 times pi over, sine of 2 times 5 pi over 6 is 10 pi over 6, which is 5 pi over 3. I need to draw a little circle. 5 pi over 3. So there's 1 pi. So 2 pi over 3, kind of like that. So this is now, I don't know if I did that right. 10 pi over 6, 5 pi over 3. Yeah, this is pi over 3 here. This is 60 degrees. And what did I want? I wanted the sine of it. So that's square root of 3 over 2. So -2 square root of 3 over 2 plus cosine of 5 pi over 6. That's this guy. The cosine here is also square root of 3 over 2 plus 15 pi over 6 minus, and now I'm just going to plug in pi over 6. Okay, so -2, I don't know, what's pi over 3, sine of pi over 3 is again square root of 3 over 2. So -2 square root of 3 over 2 plus cosine of pi over 6. That again square root of 3 over 2? It's giving me a headache. Where was I? Cosine of pi over 3. So that's, I don't think I'm doing this right. I'm up here kind of focused and talking and writing. I think I have to check this again. You know what? I think actually I'm going to take my own dad advice. Does anyone remember what that was? I'm going to go back here and I'm just going to integrate from pi over 6 pi over 2. Thinking that'll make life easier. Just going to integrate from here to here because I know this is symmetric. All right. I shouldn't have erased this, but there's no integration here, right? Yeah, there's an integral still there. So I have -2 times the 2, right? Doesn't that eliminate this? Oh, boy. Okay, I think that was a mistake. And this becomes cosine of theta plus 3 theta over 2. All right, from pi over 6 pi over 2. Okay. So negative sine of 2 times pi over 2 is sine of pi, which is 0, right? So we get 0 plus cosine of pi over 2, which is 1, plus 3 halves times pi over 2 is pi over 4. This is much easier. Minus, especially when you get the integral right, the antiderivative, sine of 2 pi times pi over 6 is sine of pi over 3. It's this guy, so that's square root of 3 over 2, plus the cosine of pi over 6, which is, again, oh wait, the cosine is going to be the negative square root of 3 over 2? Plus 3 halves pi over 6 pi over 4. So that would be 1 plus 3 pi over 4. These would cancel. Minus pi over 4. This would be 2 pi over 4, so 1 plus pi over 2. I hope that's the right answer. We're going to find out, aren't we? So now I'm going to put it back in the regular mode because I'm not asking it to integrate in that manner. So what was my original function? 3 times sine squared. This up here for you. So that's 9 sine x. You know, the last time I did this, it didn't work right, so I'm going to be careful. Sine x squared divided by 2. Yes?
You have a simple one.
I have a simpler one? Yeah, but I want to eliminate, you know, any intermediate errors I might have made.
And for the negative sine theta, for the last step, from the negative sine theta to the cosine theta. No, I mean the negative integral. From the negative sine theta to the cosine theta, you
From the negative sine theta,
can
you mean from here?
to the bottom. It should
Well, the
be-
derivative of the cosine is the negative sine.
Oh yeah.
I'm finding antiderivative.
Okay.
Minus 1 plus sine squared. One plus sine x squared divided by 2. Okay, I don't think I don't think this is going to fit our limits. Well, that's interesting. Okay, so let's see if I'm anywhere near. Okay, so the lower limit was pi by 6, and the upper limit was. Oh, you know, I think I left out my 2 also, right? So 2 plus pi for the whole thing. Okay, so pi divided by 6. Well, clearly the answer should be pi.
Because you get wrong for the cosine pi over 6, it should be the positive number from the main table.
Help you. Wait, are you talking about something over here?
Yeah, the right one.
It's okay, I just don't see it. I know there's an error. We're saying cosine of pi over 6.
It's positive, it's 3 over 2.
That's over. Okay, wait a minute. So this should be negative sine of 2 theta at pi over 6. So it should be negative sine of pi over 3. And that sine, all right. Homework assignment, find the professor's error, if you wish. Need more coffee, actually. All right. Why don't we take a break? I'll see if I can figure this out, what I did wrong. When no one's watching, and we'll come back in 5 or 10 minutes, and we have a little more to do today.
Oh, right now we're not trying to fail process?
You know where the error is?
Right now we're trying to get the hydrate. Yeah. Oh, when we transfer? Don't get true if we were to. Oh, that's true.
C's get degrees.
I don't know. I can
Okay, I'd like to make
I don't have that paper. Sorry.
再说点嘛好不好？就是片儿的片儿的。
Sorry, I forgot you.
对，我就是这把。
Does everybody have a worksheet?
对。
Hi.
我这个把旁边。对呀。
那不是陈冠希都这样吗？
We do have a whistle here. So I would like to announce that thanks to your fellow student Chris, who pointed out that the cosine of pi over 2 is 0, that the 1 went away and we ended up with pi. So it wasn't that hard, if you're awake. All right, there are just 3 problems on here. The first 2 are very simple, and the third one, it doesn't say so, but it wants the area between these curves. So give that a try. We'll look at them in maybe 10 minutes. We'll talk about them. And then we have more exciting things for today. It's amazing. We have so much exciting stuff in this class. If you don't have worksheets, let me know. Huh? No. Where are you? And Zimin? Oh. Got something? This is your new quiz score. I wonder if it's the warm weather.
Stick around. We're not selling the
No, that's not.
Let's see. Maybe I entered something wrong. Oops. If looking along the right lines though, you want to make sure this makes sense. This is yours. Keep an eye on yours because they're the same exact model. I don't see why it should, because it's just the axes. No, that shouldn't. It's just -2. I don't know know how that did anything different, but it did. Oh, because it was off the chart.
So it's off this.
Yeah, so if we go, I think, no. Oh yeah, it's off the chart. Yeah, it is off the chart. Yeah. Okay, so between the two curves, it is just a circle. You could actually just find the area decided to subtract the area of the circle. Or
So because minus this square.
yeah,
Yeah. Is that what that
should. Gotta get the limits right. Yeah. I guess we know what the limits are, 0 to pi. Oh, that's another. That's another feature of this problem, which is it's not 0 to 2 pi. Wait a minute. Yeah, it's not the whole thing. It's just from 0 to pi.
Does that change my equation?
So,
Will that change my equation?
no, it'll change the limits of integration.
Okay, but I don't have to change the sum inside, right?
I think, yeah, the equation you described is right.
Okay.
We'll find out in a minute or two.
I'm that.
Yeah.
I've become that.
Professor, how much is this midterm worth?
It's about 5 or 6 pieces of paper, so on the open market, 2 cents, is that? No. You mean how many points in the final grade?
Yeah.
I expect the teacher to know everything.
Sorry.
No, it's okay. I'm just giving you a hard time because I'm cranky. It's not your fault. All right. Website, green sheet. Midterm, 35%. 35%. It's important.
And how about final?
You want to do good? The final is 40%. 40. That's
So
70.
how many meters? How many meters? How many meters?
Oh, 1.
That's what?
Well, if there were 2, it'd be worth 670 plus 40 is 110. That wouldn't really add up, would it? Hang on. Okay, so if you want to keep working on the worksheet quietly, you can. I'm going to talk for just a second because I feel like I have something to say. And it's specifically for non-English speakers, although some English speakers might find this interesting. You may not know this, but if you're on the west coast of the United States and you say, like, can I have a couple pencils? A couple pencils. People mean usually 2 pencils. But if you're on the East Coast and you say, hand me a couple pencils, they mean a few pencils. which could be 2 or 3, or a couple M&Ms could be even 5 or 6. So not everybody knows this, but it's just a subtle thing. And I mention it because Al asked me how many midterms. So maybe it's a West Coast thing, I don't know, but on the East Coast, where I went to school, the midterm was the exam in the middle of the term.
Well, like some professors here though?
I know where you're going. So there was just one, it's the one in the middle. But you see, now we have this subtle difference in the word middle. Middle can mean halfway between the beginning and the end, or it can just mean between the middle and the end, and as you suggest, some professors give 2 or even 3. I call that a test. And I guess I don't give, the quarter's too short for me to give tests. I just give a midterm test and some quizzes, meaning, okay, that's all I wanted to. It's not that, language is curious. Even you're from America, sometimes language changes. It's a big place. In China, they have like 30 or 40 languages, right? There's a lot. I mean, I know there's the 2 main ones, right?
Just dialogues, not language. Not language, just dialogues.
Dialects, yeah. In the U.S., we'd say dialects. That's right. Unlike in Canada, where they speak English and French. Yes. I guess if you came from outer space, it'd all be just like dialects, right? All right. Let's take a look and see if I can. Something funny, but let's take a look at these. I think these problems should be fairly straightforward. Here again, what do we notice immediately about this problem? In the symmetry of it? This is an even function, and we're going from minus a to plus a. So we can always, we have a magic marker that works. We can always just go from, instead of from minus pi over 6, we can just go from 0 to pi over 6, and then put a 2 in front. And then what is our formula? It says this function squared 3 pi over 2 theta. So now we're back to this. We have to remember what the cosine squared x is, right? Now I wish I hadn't erased it. Cosine 2x plus 1 over 2. But this is now 3, so it's going to be cosine 6x plus 1 over 4. Or, well, theta. Or sine 6 theta over 24 plus theta over 4 from 0 to pi over 6. And you can see immediately when I plug in 0, I'm going to get 0. Makes things simpler. Sine of 6 theta, plugging in pi over 6, that is the sine of theta, which is 0, plus, I just plug this in here, pi over 24. Anybody else get that answer? Skeptics. Let's see.
You have to type multiply 2. You forgot that.
Oh, I forgot the 2. Oh, I always forget the 2. Let's see. In case you are wondering, when I go ahead and I check these things, you might think it's because I don't know if I got the right answer. And you would be right. However, I also check because I want you to check. Oh. I can do that, can I? So, okay, so I have the cosine of 3x squared, and I want to integrate that from 0. No, did I do that too fast? What happened? Oh, upper limit, okay. Pi divided by 6. And I want to know, oops, it's not what I wanted to do. Can I still do this? No. I'll try again. 7, 0, divided by 6. And I want to know what pi divided by 12 is. Oh, it's the same number. Good. Thank you for reminding me about the 2. It's always a good idea, if it's not too hard, to check your work. The calculator doesn't give you the exact answer, but it's sure going to tell you if you're off. Sam?
So I have a question about one of the steps here. Why can't you pull out the 1/4 as a constant? Can you pull out
It's
the 1/4?
plus 1/4. We could break it up into 2 integrals.
Yeah. Well, but either way, couldn't you just pull out the 1/4 since it's a constant in both terms? Since it's a constant in the whole thing, could you pull out the 1/4?
You're adding by 1.
Let's be really careful here. I don't want to tell you something that you're going to come back to me and say, you said you could do that. Okay, here's what you can do. You can say, here, 0, pi over 6. You can say this is the integral from 0 to pi over 6 of cosine 6 theta over, well, yeah, there are 2 still in there, plus the integral from 0 to pi over 6 of 1/4 theta. That's the only way you can pull it out. It's not a factor, it's a term, something you add.
I know, but wouldn't you pull out the 1/4 and then it'd be cosine 6 theta plus 1?
Oh, I can take out the 4, is that what you mean?
Yeah, well, I mean, it's...
Oh, yes,
yeah.
you can do
But I mean,
that.
technically, you're taking out a 1/4 from the whole thing.
Yes, absolutely.
Yeah, you can do that, okay.
Yeah, I can still do that here, right? I can just,
Yeah.
like, as long as I make sure. So this is just 1. Question? Okay. The second problem, here we've got the tangent function, which add on here, but I'm not gonna do it now. We know the tangent gets bigger. So we're going from 0 to pi over 8. So again, here we can't use anything even or odd, but we can do this. Tangent squared 2 theta over 2 using our formula. Okay, so what do we know about the tangent squared? Or should I say, what do we know about integrating the tangent squared? Know anything? Well, let's take a look at this as a separate problem. You know the tangent squared of x is the sine squared of x over the cosine squared of x, right? We know the sine squared is what?
1 over 1 minus
1 minus cosine squared x over cosine squared x. So that's 1 over the cosine squared of x minus 1. 1 over the cosine squared. That's the secant squared of x. And the secant squared should ring a little bell in your head. Derivative of something is the secant squared. Remember what the antiderivative of the secant squared is? We're going to go over that later today. So, all right. It's the tangent. So we end up with 0 to pi over 8 of secant squared x minus 1, well, theta. 2 theta minus 1d theta. Okay, so if the derivative of the tangent is the secant squared, the derivative of the tangent of 2 theta is the secant squared times 2, so we're going to have to divide by 2. And then just minus theta. 0 to pi over 8. And now the part I'm learning to hate, where I embarrass myself by plugging in. So pi over 8 into 2 theta is pi over 4. Tangent of pi over 4 is 1 pi over 4. 1. Right? I'm like happy. Pi over 4. Sine over the cosine, that's 1. So 1/2 minus pi over 8 minus now 0. Tangent of 0 is 0, so the tangent squared is just all 0 minus 0. So we just end up with 1/2 minus pi over 8. You didn't know your trig in 48C, you're going to know it now, right? Okay. Just one more here. This we definitely want to look at before we start. This is another great thing about the calculator here. You can use it to visualize these things and see what's going on before you jump in and make a mess. So here's the cosine of theta, 1 plus the cosine of theta, and cosine of theta, graphed for your pleasure. think we need to zoom in on this, because this doesn't look very good. Oh, we're not in polar mode, are we? Be very careful, you want to be in the right mode. Otherwise, things don't make much sense. Oh, there it is. All right, so did everyone see that in real time? I'm going to see if I can I'll just put it next here. That didn't do it. It's too smart for me. All right, so I'm going to do this. Before I do it, I want you looking at it. You can actually learn something by the limited speed of this calculator here, right? Watch real carefully. Okay, so what you're seeing is we're going from 0, let's see, what's our window? 0 to pi. And the outer graph goes up and around like this. But that's the 1 plus cosine. It only gets around to here. But this graph, it goes around like this, and then back around again. So we want to be a little careful about this. Anyone see what the problem is? I mean, I want this area here between the curves. Does anyone see what's going to happen if I'm a little sloppy about this? Let me show you what I mean. So my tired. My f of x is the 1 plus cosine of x. And my g of x is cosine of x. So if I just, and I want this from 0 theta, if I go from 0 to pi, I want to make sure I'm saying this right. If I go from 0 to pi with this function, it just goes kind of like this. But if I go from 0 to pi with this function, it seems to go all the way around. Huh. I'll look at my window again. Yeah, I'm going from 0 to pi each time, right? So really what I want to do is I want to measure this whole area. Let's use a different color. I want to take this area, which I can use using this formula, right? 1 plus cosine of x squared over 2 dx. Then I want to subtract just this. I don't want to subtract this 2 because that'll give me the wrong answer. So how do I do that? Well, I could be really smart. I could say, what's the radius of this? This is 1, right? The diameter is 1, the radius is 1/2. So I could just subtract pi over 4. Or if I don't like doing that, I can see that if I use this same formula here, say cosine squared x over 2, if instead I only go from 0 to pi over 2, is that right? That's what it looks like.
How do you know it's pi over 2?
You know, I'm not sure, actually. I'm now beginning to wonder if that calculator's throwing me off.
It's,
Is it throwing me off? Well, I guess I actually have to graph this manually. Let's do it. At 0, I'm just going to look at this for a second. At 0, this is 1. At, let's say, pi over 2, cosine is what? Zero. Yeah. And halfway in between pi over 4, it's square root of 2 over 2. So yes, it is just from 0 to pi over 2. Do you see how that works? In other words, cosine is 1, and then it goes down at pi over 4 to square root of 2 over 2, and then it comes down to 0 at pi over 2. And then it'll, if we keep going around, we'll get the whole circle. I'll tell you what. I know you can do this, although it's troublesome. Let's just check my theory here. Let's do this integration, and if we get half the, well, actually, it should be 8, right? Because if it's half, then the area of the circle is pi over 4, but it's only half, so it's pi over 8. So if this is pi over 8, then I know what I'm doing. All right, so again, cosine squared is cosine 2x plus 1 over 2, but there already was a 2, so we make a 4. Right? And cosine 2x, that's sine 2x now over 8 plus x over 4. And I'm hoping 0 to pi over 2, that'll give me pi over 8. Okay, so sine of 2 times pi over 2, that's 0. Plus pi over 8 minus sine of 0 plus 0, minus 0, is pi over 8, just like I thought. That's what makes these things a little tricky. You have to be a little careful. Okay, any questions about this? There'll be some homework problems due next Tuesday after you'll have the weekend. Don't do it now. Study for the midterm. Okay, any other questions? Good. So we're moving on a little here. The next section we're going to do is a little bit vague. Well, the next big section we're going to do is about techniques of integration. We've really learned, let's go over what we've learned about integration. First thing is, find the antiderivative. That is, find it kind of by inspection. So if I want the integral of x dx, you think, well, I know x has to be the next higher power. So it's going to be x squared. But then, I find the derivative. The derivative of x squared is 2x. This was only x, so if I start by dividing by 2, I'm going to add my integration constant, then I get the right answer. So I can look at a bunch of derivatives and immediately know that if I go backwards, I get the antiderivative. So, for example, a little table here of some common derivative, antiderivative pairs that you should know. The first one we showed up in a problem already today. Secant squared. The integral of the secant squared is the tangent, or if you like, the derivative of the tangent is the secant squared. Similarly, if we take the secant of x, which is 1 over the cosine of x, or if you like, cosine of x to the minus 1, we can just use the chain rule and find out this is minus 1 cosine of x to the minus 2 times the derivative of the cosine, which is the negative sign. So that just gives us, the minuses cancel. Sine over cosine squared of x, which is sine over cosine of x, times 1 over cosine of x equals tangent of x times secant of x. So that's another handy one. From the derivative of the inverse sine, the derivative of the inverse sine is 1 over the square root of 1 minus x squared. Everyone remember how we derive that? I'm just going to give you a little hint, which is dy dx. This is a formula you should know from first semester, is 1 over dx dy. So if you want to find the derivative of the inverse sine, you instead find the derivative of the sine and play around with it, and you get this formula. The rest of these are not so obvious until we get down to the derivative of the inverse tangent, 1 over 1 plus x squared. This is, in a later technique, this is going to become very important, but it's good to know some of these. There is another technique, which is not, I guess I'm stretching the meaning of technique here, which is in the back of everyone's book, I guess that's where I'll find it, you'll find a table of integrals. Let's see if I can. Table of integrals. This is a 3-page table of integrals. It has 106, you go down to the bottom, different forms. If you have some complex integral, and we're not learning specifically a technique on how to, under Nate, how to solve these, you might look them up in a table. Perfectly legitimate. We want to know how they got these, which is why we're going to be studying more about finding integrals. But in the real world, if you're out there doing your, your business calculation or your physics or your chemistry calculation, you don't always have to sit down and grind through an integral. You can sometimes look it up. This is a second method, tables. This, by the way, is actually a very short table. If I remember, I'll bring it in. I have a book at home. I think it's got at least 500 or 600, maybe it has 1,000 different integrals, and it's many pages. The problem with a table that long is then you spend a lot of time looking something up. You have to find the right category, and then you have to find something that looks like what you're doing. Of course, that can be better than finding nothing. So that's another strategy. The third strategy, which we won't use much in this class, is we use a computer system. If you invest in the next level up of TI, I think 85 maybe, and thereon, they'll have a function where you put in an integral, and it doesn't find it numerically. It will try and find the actual integral, the actual antiderivative for you. It'll also do derivatives that way. That's one way to do it. Can be a little awkward, and if you're not careful, I think I told some of you the story about a high school calculus student I had who turned in his final with all sorts of weird constants. And it didn't make any sense to me because he was not supposed to be using a calculator until I realized he was in degree mode and not radian mode. So, for example, if you find the derivative of, say, sine of x, but x is in degrees, then you don't get cosine of x. If you think about it, well, x is in degrees, then what? X times 2 pi over 360 equals theta radians, right? So theta is equal to, or x is equal to theta times 360 over 2 pi. So if you plug that in, the derivative with respect to x of the sine of 360 over pi theta is the cosine of 360 over pi theta times the chain rule 360 over 2 pi. And that's, and then this becomes x again, of course, but that was the kind of answer he was giving me. And he didn't even realize there was something seriously wrong. So, again, a technique that has advantages and some disadvantages you can overcome if you're careful. Okay. So, and of course, we've already seen substitution. And we're going to go on, we're going to find a few more techniques. But what we're going to look at for today are some examples where we already have all the knowledge we need to do them, but we need a hint, right? We need a hint. So, I'm not going to assign this comes back to a question of how do you teach math, right? I can give you formulas, I can show you strategies, but a certain amount of math is just getting in there with those equations and thinking, I know there's an answer here somewhere. Let's think of something we can try that might make this possible. So, for example, if you started off with an equation, an integral to solve like this, 1 over e to the x plus e to the minus x. Well, that's very nice. Those of you who've been paying attention know this is 1 over the hyperbolic cosine, which is the hyperbolic secant by definition. But it's not really clear how we would find the integral of it. We need some help. We need some kind of trick. And the trick here is to notice that if we multiply this by, I don't really want that multiplication sign here, e to the x over e to the x, then we might get something we can deal with a little better. Over e to the x plus e to the minus x minus x. What does that come out? That becomes e to the x over e 2x plus 1. Now you might think, does that help me any? I don't know. But you can see that the derivative of e to the 2x, that's e to the x squared, right, involves the product rule and the chain rule. Just going to throw another e to the x out there. So we might want to try some kind of substitution. In this case, let's try u equals e to the x. So we find du equals e to the x dx. That looks good. And when we plug this in, we're going to get du over u squared plus 1 du. Well, everyone should already know what that is by now. That's tangent inverse u plus constant. And when we plug back in, we find that's tangent inverse u x plus a constant. So I think all those steps were straightforward. The real hard part is knowing, when to apply this trick. So when should you apply this trick? I don't know how to teach that. You do some homework problems, you get a little practice, and you get a feel for it. And then you know. Or you don't, and you guess. Okay. Let's take a look at another problem. This one, completely different issue. So the question is, how should we approach this? Well, when you see a lot of trig functions here like this, it often helps to reduce things to sines and cosines. That way, you can get a better idea what you're dealing with here. So let's try and do that. This is the cosine of x plus sine cubed x over the secant. That's 1 over the cosine of x. Well, inverting this, we get what? Cosine squared x plus cosine x sine cubed x. Well, that looks much better. To begin with, we've already done this problem 3 times today, right? That's just going to be the integral cosine of 2x plus 1 over 2. And we're going to do a whole section on trig substitutions, but you might already suspect here that if we do a substitution where we let u equals the sine of x, so du equals cosine of x, that this is going to become u cubed du, right? And this will become u to the fourth over 4, which will plug back sine of x. So it's just going to be, this is just going to be end up sine of x to the fourth power. Sine of x function to the fourth power, not x to the fourth. Okay, so that's another strategy. Convert your sines and cosines, your trig functions to sines and cosines. See if that doesn't help. These are kind of an eclectic group of techniques we're showing here, and we're kind of squeezing them in because you look at them and you get an idea and you put it into your bag of tricks, and you do a few homework problems and practice them a little, and shortly thereafter you're an expert. Okay, here's another type of problem where a simple solution, a difficult looking problem can be simplified. If you have a rational function like this, where the degree of the numerator is greater than the degree of the denominator, sometimes it will help you to do some division. So I hope you're all familiar with this kind of division. So this is x squared plus 4x minus 2x plus 1 minus 2 minus 2x minus 8. 1 minus 8 is that right? Well, 1 minus 8 would be 9. What this means is this should be integral x minus 2 plus 9 over x plus 4. But since my piece of paper says something different, I'm going to double check it. Multiply x minus 2 times x plus 4, so negative 8, or x minus 2x, x squared, so it's x squared minus 2x minus 8 plus 9 is 1. Oh, okay. All right, so what do we do with this? Oh, now this is easy, right? This is just x squared over 2 minus 2x plus, what do I do with this? This is 9 times what? It's the integral of 1 over x plus 4. I mean, I could substitute integral 1 over x plus 4. U equals x plus 4. Du equals dx. So this just becomes 1 over u, du, which now you should all know. The log of absolute value of u, or the log of absolute value of x plus 4. Okay, so that's another strategy. Take a rational function and divide. And I don't really have time to do two more. So I'm going to take the easier one. And we'll take a look at the last one on Tuesday. So there we have an integral 1 over 1 plus cosine of x. And again, we're gonna try and find something we can multiply this by that might make it work out a little better. So in this particular case, we're going to magically pull this out of my hat. We're going to multiply this by 1 minus cosine of x over 1 minus cosine of x. And the reason is because I end up on the bottom with 1 minus cosine squared x, which of course is just 1 minus cosine of x over sine squared x. I'm going to break this up. 1 over sine squared x plus cosine over sine squared, that's cotangent times cosecant. And this, of course, is secant squared, which we talked about earlier. And there you go. Is this on my chart here? Oh, no, it's not. Well, secant times tangent is. It's the secant. And I think you'll find if you look in the tables in the back of your book that cotangent times cosecant is probably negative cosecant. So again, here's something we don't have any idea what to do with, but now we can turn it into something we can know, we can understand. All right, that's it for today. Good luck, study hard. If you have any questions, I'll be here for a little while. As long as I need to speak. That doesn't mean